Welcome! In this presentation, I will explain how to combine multiple zoom levels to enable large context windows in neural networks. In a way, we will be showing the networks to see the bigger picture. Let's briefly revisit the current state of deep learning in remote sensing. These days, we use deep neural networks for a wide range of tasks, like the automatic classification of scenes, segmentation of imagery, or the detection of objects. Given enough data, these models can perform amazingly well. But it is important to keep in mind that they were originally developed for a slightly different use case. These models weren't built to work on aerial or satellite images, but instead to work on ground-level, photography-like imagery. This doesn't mean that the models cannot be used for remote sensing imagery, but we need to be very careful about the assumptions that went into these models. To understand what I mean by this, let's look at an example. The convolutional neural networks, or CNNs, that we use today are tweaked to perform well on datasets like ImageNet. Here, the relevant objects are constrained to the image. In the image on the left, for example, it is easy to see that this picture belongs to the sheep class. And zooming out rarely reveals any useful information for this kind of imagery. On the contrary, if we zoom out, we might actually confuse the model when new confounding objects come into the frame. Now, when we apply these methods to our remote sensing imagery, the story is different. Most times, the scenes that we are working with are too large to fit into the GPU memory, so here, as well, we have to cut the imagery into patches. Due to lack of a better method, this is usually done in an arbitrary fashion. We fix a patch size in the stride and just cut away. But this means that important information might be lingering just outside our current patch. Look at this example on the left. It's a street of some sorts, maybe a highway, we can't really tell. But once we zoom out, it becomes pretty clear that this has to be an airport runway. So when we work interactively with such imagery in GIS programs, zooming in and out is something we do almost subconsciously to combine a spatial overview with high-resolution imagery. And yet, we do not give our AI models the opportunity to do just the same. And as I mentioned, this has to do with this limited memory, right? So in a perfect world, we would just increase the patch size to some huge number and call it a day. But sadly, the machines that we work with have these limitations in memory and computational resources, so we have to make it work somehow. And as much as we'd like to, we can't simply keep increasing the size of the patches that we feed into our networks, because once the memory is full, it's full. But maybe we can find a clever way of engineering our way around this limitation. To get there, it's very important to understand the difference between the two processes of extending a patch and zooming out. Intuitively, they appear to be the same, but when implemented in computer code, they do different things. So let's see what happens. In the first case of extending the patch, we leave the image at the same resolution and merely add new pixels at the edge to reveal new context. This is the memory inefficient approach that is exhausting our GPU memory. On the other hand, zooming out reveals new context by reducing the image resolution. This means that the total number of pixels stays the same, but we can still get an impression of the context around our original tile. Now, after clearing that up, we realize that we want to build our framework around this second approach, the zooming out. So let's take some inspiration from existing works. Here's a schematic of the very popular UNet architecture. An integral part of that network are the down and upsampling steps, denoted here by the down and upwards facing arrows. This is already very similar to what we had in mind. But here, the downsampling doesn't reveal any new context. Instead, the downsampled feature maps simply have a smaller size. So what if we extend this downsampling step to a full zooming out step? This means that we extend the feature maps at lower resolution levels to match the full image's size in pixels. And by doing so, we reveal a much larger spatial context. Here, you can see a schematic idea of our proposed architecture. On the left, we have 4 images centered on the same location, but at zoom levels of 1, 2, 4, and 8 respectively. The green square in the lower images indicates the spatial footprint of the highest resolution tile. Now what this network will do is it will start aggregating contextual features at a very low resolution, but with a very wide spatial context field, and then work its way up to the higher resolution levels. Finally, we will then get a prediction at the full resolution level that is not only based on the current tile, but also on a large spatial context around it. Let's look at the same thing a bit more in depth. Initially, we have to prepare our data for this network, and you can think of this process as cutting tiles from an image pyramid instead of cutting them from the image directly. At the very beginning, we start by cutting 4 patches of different sizes from our satellite image. You can see this symbolized here by these 4 colorful squares on the left. The large blue square is taken at a very low resolution, and the tiny red square at the full resolution. We choose the sizes of our crops in such a way that in terms of actual pixels, each patch has the same size. Then we take these 4 images as inputs to our network, where we initialize feature maps with a convolutional block for each resolution level. Then we start this merging procedure from the bottom. At each step, the lower resolution feature map is merged with that of the next higher resolution level. To map the same spatial locations together, we have to crop the central part of the low resolution feature map and upscale it. Then we can simply do an element-wise addition to merge it with the features from the next resolution level. And after doing this for 3 times, we arrive at the full image resolution. Now we have these very rich features that include detailed information about the tile, as well as rich contextual information about its surroundings. Now we just add 2 more convolutional blocks and we get the final prediction of the model. So, what's the point of all this? Let me introduce you to an application where spatial context is tremendously important: sea ice charting. Here is a Sentinel-1 image of the west coast of Greenland. To the right, you can see the actual land. Left of that we see a strip of open water, until finally we observe a large patch of sea ice towards the left. The edges of these regions seem very well defined in this overview image, but the story is very different once we zoom in. Here's a full resolution image of the border between open water and sea ice. Can you spot the exact location of this border? It's hard to tell, isn't it? Here's the corresponding ground truth. Things get much easier once we start zooming out. And remember, this green square is the original patch that we were interested in. So we trained our model on this dataset and gave it access to these 4 zoom levels. Let's see how the results compare to the baseline set in the original dataset paper. We follow the given evaluation protocol that suggests 2 different methods of training. In the first one, we train the model to directly predict percentage of sea ice cover present at each pixel, so it predicts values in the range from 0% to 100%. The second method is to train on thresholded data, where the model only has to predict if any sea ice is present, making this a yes or no question. Then the accuracy is calculated for both of these approaches. And comparing to the original results, we can see that this contextual approach indeed improves the performance considerably. So let's look now at a visual example. Here we see a SAR image, the corresponding ground truth, and the prediction by the 2 models. Circled in red is a large iceberg, which has some confounding texture when looked at on the highest zoom level. However, when we zoom out further, it becomes pretty clear that this is indeed sea ice. This is a very good example of a location where the improved context can greatly improve the model performance. So, let's wrap up. The number one thing that you should take away from this talk is that remote sensing needs customized deep learning models, instead of applying only whatever model might be the current state of the art in computer vision. We should therefore unite existing ideas. For example, the idea of image pyramids, with the amazing learning capabilities that deep learning offers. Also, keep in mind that we didn't spend any time tweaking or optimizing our model, and the unoptimized contextual model still outperforms the tweaked computer vision model, so you can expect much more to come here. Thanks a lot for listening to this talk. If you want to have a test drive and play around with this idea, you can find our model and training code at the link below.